my pleasure to introduce our speaker, Herve Bourlard. Of course, there's no need to introduce him because he's well-known here at CSP and we're in the speech recognition field. So Herve started in Belgium, was a professor at Mons, and then he's now at IDEA in Switzerland, where he directs a team of researchers in various fields, including speech recognition plus others. He also works closely together with Nelson Morgan and others at Dixie. Today's talk is about non-stationary multi-stream processing for robust and adaptive speech recognition.
Okay, thank you. I don't know whether I should stand here or there. Yeah, I think it's better, yeah. Anyway, thank you for inviting me. It's my pleasure to give this talk. I apologize to people who have already heard this talk several times before or who know pretty well what I'm doing these days. But even for those people, I promise you that there will be something new during the last 20 minutes or so of the talk. Anyway, if you want to visit us, you are very welcome. Just this, you have a little picture here. It's not very clear of the city of Martigny, which is about 20 minutes south of Lausanne, so south of the lake, just below Montreux. For people who are expert in jazz, there is a famous jazz festival there, just on the lake of Geneva. So this is just south, at the middle of the Alps. It's sunny, and it's a nice place. So you are very welcome to come whenever you want. Tomorrow, yeah. So this is the outline of the talk. There are many points, but I'll try to make it short. I'll try to skip equations and to give you a flavor of what we are doing, what we call multiband, multi-stream, ASR, automatic speech recognition, what the people are talking when they mention this product of errors rule, and what we call now full combination multi-stream, multiband, which gives very, very, very good results on narrow band noise. Reliability weighting, unsupervised online adaptation, some recognition results, and now this new theory, which is a generalization of multiband that we called HMM2, which is an HMM mixture. So it's a mixture of HMMs, and we will show you how it performs for a Foreman-like tracking, and also their use in robust recognition with very, very few parameters, like 3 parameters as features. So this talk requires a minimum of background in speech recognition, so I don't expect me to talk about HMMs and EM training. I expect that everything is very well known here. So, but this is basically what people are doing in standard HMM recognition or speech recognition. So we have a sentence, we have a spectrogram here. Every 30 milliseconds or every 10 milliseconds, we extract a feature vector, which is a spectral vector. Okay, and we do some transformation, MFCC or whatever you prefer, and we send this 10 millisecond vector to the recognizer, to the HMM. Of course, if there is noise in one band, the whole vector is usually corrupted, especially if we do MFCC where we orthogonalize the features and then we spread the noise everywhere in the vector, even if we have noise, a narrow band noise. So if there is one band noisy, basically it's going to contaminate your probability density function, and the recognizer is going to collapse, as we all experienced several times. So the general idea of multi-stream or multi-band. So when I speak about multi-band, multi-band is a particular case of multi-stream. Multi-stream is basically we are looking at a problem where we have several streams, data streams, okay, representing the same phenomenon, but we have several streams which are not necessarily synchronous, which don't necessarily have the same frame rate. Okay, and we want to use this information to recombine them to do recognition or classification. Multiband, it's a particular case of multi-stream where we are going to look at the signal in different frequency bands. We process each band independently of each other, and at some point in time we recombine the bands or the likelihoods of each band to yield recognition results. Okay, so if you look at the K-stream HMM recognizer, it looks like this. So we have parallel HMMs with possibly with different topologies, okay, which are going to recombine their likelihoods. At some points here, this is not an HMM state, it just means recombination of likelihoods. And sometimes it could be a product of likelihoods, or sometimes it could be something more complex than that, like a weighted sum of likelihoods, also known as mixture of experts or whatever. The advantage of product of likelihood is that if we have a product of likelihoods here, we can distribute what is happening here on each state locally. And then it boils down into something that's tractable, easily tractable, which is called HMM decomposition or HMM recombination. So HMM decomposition was already invented several years ago by people trying to basically recognize speech as a combination of speech signal and noise signal. In that case, they decompose one signal into two HMMs. Here I call it HMM recombination, although it's exactly the same algorithm because we just do exactly the contrary. We have many streams that we recombine in a single model. But it's basically the same algorithm. So there are several advantages, but still open problems. So first, this way of looking at the problem is a principal way to merge different temporal knowledge sources. We can deal with multiple time resolutions with different levels of stationary properties. What does it mean? Usually when we have multiple features, we put all of them in one acoustic vector, and we assume that they follow the same stationary property, so that it means that it's all stationary at the same time, and we feed them to HMM doing this piecewise stationary assumption. Now, if we look at the features that we have in our acoustic vector, typically instantaneous features and delta features, they are never stationary at the same time. As I was talking to people this afternoon, you know, if you look at the instantaneous features, if they are stationary, the deltas are not going to be stationary. And if the deltas are stationary, well, and if the instantaneous features are not stationary, the deltas may be stationary. But they are not stationary at the same time. So looking at those streams as independent streams processed with independent Markov models, recombining their likelihoods over at some point in time, helps to solve this problem of non-synchronous stationarity properties. Okay, multiband, the advantage is potential noise robustness and so on. There are still open problems how to do signal processing in those subbands, although this has been investigated quite a lot yet, and we know more or less what to do there. And the combination criterion. This is still a very important problem, how to recombine those streams, according to what criterion. So more recently, Mr. John Allen, you know, from AT&T, I'm not going to come back to this, which is quite known and quite controversial, and I'm not going to get into the controversy, but John Allen, following results of Fletcher in the 50s, I think, came up with this psychoacoustic evidence. Sometimes I call it product of errors rule, but people complain, especially statisticians, although I think I know a little bit about statistics. Also, they complain that it is not a rule, it is just an observation, and I am ready to agree with them. But basically what it says is that if we have two observation streams, X1 and X2, basically the way the human being recombines the streams is not by multiply likelihoods and picking up the highest maximum likelihood, is basically by multiplying probabilities of error. So basically the probability of error looking at the complete signal, ET, of a phoneme or a word, Q, given the two streams is equal to the error of the word given the first stream times the error given the second stream. Okay? So, and as we know, the probability of error is equal to 1 minus the probability of being correct. 1 minus the posterior probability, not the likelihood, the posterior probability. So we get something like this. Okay, and if we multiply them, we get a combination rule like this one, which is an interesting one. It's already nonlinear. It's simple, but it's nonlinear combination rule. So we turn this product of error rules into posterior probability rules, and we get something like this.
And what should we think of X as being? I mean, what is it?
So it could be, X could be one particular stream into several streams. So audio, video. And we all know about this McGurk effect and so on. So if we look at the video and the audio and they don't say the same thing, we are going to listen to hear one or the other, depending on different conditions. So this is basically what is happening here. You are going to pay attention to one or the other. Or you are going to rely to the stream that sounds or that looks most reliable. And that one is going to take all the probability mass, let's say. It's going to weight more for the decision. In the multiband system, X1 is a particular frequency band. So it's a subband, okay? So this would tell us how to recombine the frequency bands optimally. Okay, we can generalize it to 3 bands and so on, so the equations are obvious. In the papers I published recently, I give those equations explicitly, although they are very easy to compute, to get. But you will see that it is important for the future because actually, although this is not well formulated in terms of statistics, I'm going to show you something that we did, that we call the full combination rule for recombination, which boils down into exactly something like that, and which is perfectly correct from a statistical point of view. Okay? Now, something interesting about the product of errors rule is that if you look at what it means, this is a strange plot, but basically it represents the posterior probability for one of two streams. It's more difficult to represent it for 3 streams or more. But so if basically it shows that if I am correct, so this is the posterior probability for stream 1, the posterior probability for stream 2, and these curves give me the equal probability of correct recognition given those 2 experts. Okay, given the rules that I just expressed there. So this curve tells me that above this curve, I am above 90% correct, whatever the value of P for P1 here, or well, whatever the value of P1 or P2 is. So I can be higher than 99% correct for one expert yielding a posterior probability of 95%, and even the other one yielding a probability of only 0.05%, which is not possible with likelihood-based systems. So as soon as I have one of my experts yielding a very high posterior probability, I can achieve, if I implement a recombination properly, I can still achieve very high classification rate. Okay? So this is what it means. So just in understanding what this means, we can draw some conclusions. You know, I haven't said anything yet, but basically subband-based ASR training should minimize the product of error rules, but we don't know how to do it, but I will come up next with a good approximation to that. Ideally, a subband error rate should be independent, obviously. Subband ASR system should use a large number of subbands, because what you can prove theoretically, but it's easy to get, the idea that when I start increasing the number of experts, this area here above a certain threshold, like 0.9, so all this area here will yield a recognition rate higher than 90%. This area is going to increase exponentially when I increase the number of experts. So this area is going to be, so only for 2 experts, this area is already 30% of the space. If I have 3 experts, this area is going to grow exponentially. So more experts I have, more probable it is that I will get a very high recognition rate as long as I can implement this rule. That's what I say here. So ideally they should be independent. Yeah.
That's the case, that you can't just get to that.
Exactly. So subband ASR should be able to estimate subband posteriors as accurately as possible, and easy to implement, and so on and so on. This is the detail that I can skip. Okay, I'm going to skip the discussion about posterior probabilities, but for people who are familiar with our previous work, you will believe me that we can estimate posterior probabilities quite reliably. This has been done during the last 10 years, and so on. Okay, based on this standard subband recognizer, which is what most of the people these days are doing, so I'm not going to talk much about it because we are doing something much better than this, but this is what Hinek, my friend Hinek, is doing for the last year, 2 years, and he has got the best results on this Aurora task for the last 2 years, being like 65% better relatively to the second best partner or competitor. So this works very well, and this is what they are doing, except that they are doing it for multiband or multi-stream. And here I explain it for multiband, but we know that we can do it for any well, this is a particular case of multi-stream. So speech, we have the spectrogram here. We split it into several bands. Here just 2, but in reality, we are using 4 bands. Hinek is using 7 bands. We feed each band to a different posterior probability estimator. So we estimate the probability of a phone given the subband. So this is typically done with a neural network, multi-layer perceptron. We can also do it with Gaussians, except that we don't estimate posteriors there. So from this, we recombine those 2 probabilities to get an estimator of the phoneme given the full band, and we send this to an HMM. Okay, this is the standard thing. Okay, this works. I could talk for hours just about this one, you know, how to recombine it and so on, but there have been several papers around, so I'm not going to waste my time on this one, and I'm going to move directly to something more interesting. The problem with this one is that, yeah, there is also something that we have to know, is that in parallel to this, there has been another theory developed by several people, including MIT, Rich Lipman, and other people in England, called a missing data theory, where they show, but they were cheating because they didn't know exactly how to do it, but they were showing that if you know, suppose you have noise in one of those bands, if you know where the noise is, you get extremely robust systems if you just disregard the noisy band when you compute the probabilities. So you know, so you have 20 bands, you know that you have noise into the 15th bands, you compute a marginal distribution instead of computing the full distribution. So you just remove the noisy band when you compute the emission probabilities for HMM. So you remove it if you know where it is, and you compute the emission probability and you feed it to an HMM. It's extremely robust to any kind of noise. They really tried many kind of noise. Basically, there is no difference in performance, whatever the noise level is. So this is what we were trying to approximate here, but without knowing, without cheating, without telling the system where the noise is. But this system actually was not a good approximation to the missing data. So that's why we came up with what we call the full combination approach, subband approach, which baseline idea is very simple. Actually, suppose we have 2 bands, and I know that I have noise in 1 band, or 2 bands, or 3. I know that I have noise somewhere, but I don't know where it is. So basically, I introduce a new hidden variable in the EM sense. We all know about EM. I introduce a new variable, hidden variable, which is a pointer to my noisy bands. So it's a number telling me where the noisy bands are. And I integrate over all position of the noisy bands. Okay? So then you get into what we call the full combination, sorry for the equation, full combination subband recognizer. So if K is the number of subbands or streams, S is the set of all possible subband or substream combinations. Okay, so if you have capital K subbands, you have, if you have K, 4 subbands, you have 16 subband combinations. So if you have capital K, you have 2 to the K possible substream combinations. So 4 is 16. 20, it's, I did it, it's about a little bit more than 1 million. It looks a lot, but it's feasible still, even with 1 million possible combinations. So capital S is the set of all possible subband combinations. Then I can rewrite my emission probability here, so my posterior still. Probability of a state, Qj, given the full band, or the whole set of streams, and given the parameter space, is equal to the sum over all my missing variables, all my possible subsets there of subband combinations. So it's a sum of this thing. Okay, we all know about this, right? So we can express this as a sum over all possible subband combination of my posterior probability of a state given the subband and the parameters of that subband, times the probability of the subband given X. What does this mean? Actually, this is the reliability probability. This is the probability that this subband is the right one. This is the prior probability that the subband is the right one. It's in terms of the mixture of experts, given the observation. Okay, so these are the combination weights. There are not many of them. If we have 4 bands, I have 16 possible combinations, so I have 16 possible weights. This is not too bad. So this is what we call the full subband combination. So if we have 4 bands, it means that we have to train 16 possible classifiers working with the 16 possible subbands. So yeah.
P of S developed given X, that's the probability of one combination of subband?
Yeah, this is the probability of one subband, particular subband combination. Yeah, it's one possible, yeah, after this set here. So this is the set of all possible subband combinations. So this is the probability of one subband combination. Yeah,
The subbands are the ones that are okay or the ones that are noisy?
it's up to you, actually. You can define it as you want. They have this one is to sum up to 1. To have this correct, this probability is to sum up to 1. So usually, so they have to be exclusive and mutually exhaustive. So we defined it as experts, and we defined it as the probability that this expert is better than the others. Or we could say it's the probability that it is worse than the others. It's up to you. It's a right? So in our case, we will say this is the probability that it's better, that is the one I'm looking for.
Is there further time because there is an SL and there is an SL complement, so to speak?
Well, it really depends how you define this P of SL given X, I think.
No, what I'm saying is your P, you use further structure in your P. You said you can estimate it from data. So
Yeah, I'm going to estimate it from data. Yeah, I'm going to maximize the likelihood. So this thing is going to train in unsupervised. There are not many parameters. I assume that all those things are fixed. I train them on clean speech. They are good. When I add noise, I don't want to change my emission probabilities. They are still okay. I just want to disregard some bands. So I can do very quick online unsupervised adaptation to maximize the EM adaptation, maximum likelihood adaptation. And I will optimize these guys to maximize my likelihood.
what I'm saying is there is more structure. In other words, I don't think of P as just a probability measure on 2 to the K elements. Because if S sub L is reliable,
Yeah.
then its complement, the other subbands, that set,
Yeah.
for example, is
So these things sum up to 1. So that's what you say, right?
no, but more than that, if one is large, I would expect the other to be small.
Well, they sum up to 1. So
No, there are more than one ways for them to sum up to 1. There are people indicate something.
so maybe.
So when you're estimating it under EM in that way, it's sort of a maximum entropy type approach. It's going to try to make it as flat as possible. Right? It's going to try to make the distribution of the possible subsets flat.
Why? It depends. It's going to depend on this value. This is not fixed.
That's not.
Well, if you have noise, this one is going to decrease.
But amongst all of them, there's probably a large number of.
Yeah. Well, I'll show you the distribution. Anyway, I'm just keeping all the maths and all those. We can discuss this further. This is just an overview, and there is much more coming. So basically, this general full combination subband recognizer looks like this. So we have, in the case of 2 bands, again, usually we use 4 bands or 7 bands, but we are going to build up all the possible combinations. So there is one neural network with the empty combination. No bands are reliable. So these are the priors only. This comes from the equations directly. One expert looking at the first band only, another expert looking at the second band, and another expert looking at the 2 bands together. Okay? And then we recombine them, and we train the recombination, okay? And we feed this to the HMM. So this is the right way to do it, I think. Okay, if you stop me all the time.
Are you address also the problem when K is large?
I am coming to that. Because obviously, in our case at least, we like neural networks for many reasons. So here it was good theory, but it was a bit frightening because basically if we have 20 critical bands, we have 1 million classifiers, so we have to train 1 million neural networks. If we have 4 bands, which is what we have already 16 neural networks to train. So we did it. 16 is feasible, but we didn't like it, but for sanity check, we did it, and it works very well. But then we still didn't like it, so we came up with an approximation to that. And this is, again, sorry for the equations, but I can explain the equations without looking at the equations. What we do, you are going to understand it very easily. When we have this recognizer looking at 2 bands, we reintroduce the independence assumption. between bands. Okay, this means that we can approximate this one based on these two. Okay, so we have 4 bands. We train, as we used to do, 4 neural networks or 4 classifiers. And then for all the combinations, we can compute the probability of the recombination from those 4 that we have, from those K classifiers, assuming that they're independent then. So this is what we call the approximation of the full combination. And so we did that. So for each of those probability for a subset is a product of the subband belonging to the subset of, well, you can show this. This is the weighted posteriors and so on and so on. And you end up with a rule like this. Okay? Forget about the equations. But now what is very interesting, take the time to look at the equations. I don't have time to do it here. But these equations looks very much, so it's a sum of a product. And it looks well, it's basically the same than this product of error rules that I showed you at the beginning. It's the same equation. Except that here I have 2 capital K terms. In the product of error rules, I have 2 capital K minus 1 term, because I have the term which is missing is the prior probability. So where I don't look at anything. So I don't know whether it's because there must be a difference, or whether Fletcher was wrong, or whether I am wrong. But we have 1 more term. Okay? That's the only difference. Okay, this is what I explained here. So the full combination approximation is this. It's the same form than the product of error rules, except that we have 1 additional term. And so another difference is that in Fletcher...
Which one is where in that equation?
Well, it's up. Yeah, it's where is my equation there? Yeah, it's here. So we have all the oh, sorry. Yeah, you asked me to stand here. Okay. So you compute all possible subset combinations, and in set theory there is also the empty set. Okay, that's and in the case of the empty set you just got the priors. So we have this, and the other difference is that in my full combination approximation, all the weights are positive. Not necessarily between 0 and 1, because there is this scaling factor here appearing from the computation. So between, they are all positive, while in the Fletcher rules, they may be positive and negative. Okay? But this is maybe not important. Okay. So I'm not going to, because I still have more to say, many more. So this has been done tried by many people. All the results I have seen so far, and there have been many, and there are more and more, are very conclusive, saying that this works very well, it's very robust to narrowband noise. It doesn't hurt in case of clean speech, or very little, and so on and so on and so on. So, but just to give you one example, I'm not going to come up with many tables of results and so on, but this is the most funny one that I show to my funding agencies and so on when I need money. You know, you are just playing a very loud sound of siren. Siren? What do you say? Siren? Siren sound. So it sounds like changing. So it's very high noise, changing at random over time and over frequency. Okay? It's pretty tough. And without doing much, so this is J-raster here, so we compare with J-raster, and J-raster is known to be pretty good. And this is coming from Hinek, so I guess there is no bug there. This is the original subband performance. And these are the 2 full combination systems. I don't have time to discuss here, but there is one where we train the weights, and another one where we don't train the weights. And actually, surprisingly, but I can explain why, training the weights doesn't make a big difference. So even if you don't train those weights, you get a significant improvement. And so this is the red curve. Okay, so red curve, full combination, multi-band approach.
What do you do if you don't clean the weights?
They are all equal, uniform weight, summing up to 1. Okay, so this is 0 dB siren noise. It's pretty bad, and it's good. It's very good. Okay, this is what Hinek is using now with multi-stream and so on. So for static, for reliability weighting, since we are talking about this, So we tried many things. So the first simple one is what we call static weighting. So those weights are P of SL given X, right? So methods tested include equal, and this works pretty well, equal weight, least mean square, relative frequency correct. I don't like least mean square and relative frequency correct because this is very task dependent actually. So it's going to work on one kind of noise, but you have to retrain them when you go to.
The word relative frequency correct.
Yeah. So basically, it's we do a matching, Viterbi matching on the on the training data, and we count the number of times it was correct, and so we weight depending. So each band, you know, so you have a different classifier for different bands. So we look at how many times each band was yielding the right phoneme, right recognition. And we weight the different experts according to that. So dynamic weighting, including estimated signal-to-noise ratio in each band. So there are all those methods based on histogram and so on to compute the signal-to-noise ratio. So computing the signal-to-noise ratio in each subband and adapting the weights accordingly. Harmonicity index, this works very well actually. But I don't like it very much either. You know what it is? No? Okay. It's. Sorry? No. If you do narrow band spectrogram, so in one band you have several the harmonics of the pitch. So you basically compute how many harmonics you can see. Well, how good the harmonics are, and more you have noise, less you see the harmonics in the spectrogram. But I don't like it very much. Signal-to-noise likelihood ratio, this is very interesting, but it doesn't work all the time. So the one that we prefer now, which is the easiest one, and it works very well, it's unsupervised online. I don't talk about offline, maximum likelihood adaptation. So we fix all the parameters, okay, of the emission probabilities, so artificial neural network or Gaussians and so on, and then we compute the weights according to a maximum likelihood criterion. So it's unsupervised, online, maximum likelihood estimation, okay? So just to give you an example, this is what we get if we do it on clean speech. This is pretty noisy, well, strange graph. This is one of my students who curses to do that, but don't like it. So we have the 20 phones, and we are computing the different weights for the different bands. So these are the weights for the 4 bands. Okay, for different phones. And if you look at this, you know, you see that for this one, probably this is a fricative. This one also, this one. There are a few fricatives where the 4th band is emphasized. And for other bands, these are vowels probably and so on, where you have the first and...
I didn't get, what is the model of the noise? In other words,
There is no model.
No, but I mean, what are there's got to be some statistics of how frequently the noise is in this band, how frequently it's in that band.
No, because, no, not at all. We just assume that it is a narrow band noise. So the noise is somewhere. We don't.
Noise, but still, how is it?
Well,
itself?
if you add noise to, you train a classifier on clean speech in one subband on clean speech.
Fine.
You have a classifier. You don't change the parameters. If you add noise, the likelihood is going to decrease.
Yes.
If you are lucky. It's not always the case. For some type of parameters, it doesn't happen, actually,
Okay.
for MFCC. But for spectral vectors, it happens. So the likelihood decrease.
Yes.
So just based on this, you can measure. So the likelihood decrease, so it's going to have less impact on your recognizer.
But don't we have to have a statistical...
No.
I mean, there's a random process which puts in the noise, right?
Yeah.
It may favor a particular band.
It may favor a particular band. Why should it favor?
They prefer to be in the high frequencies.
Put it another way, is there a statistical model of speech and noise for which this procedure would be the optimum encoder?
There is a model for speech.
I know what I'm saying. Is there a model for this sort of censoring process or this chopping out of
No. We don't need anything like that.
what you need it? It's just formalize the problem.
I'm not sure I understand the question there.
Well,
So
I guess
if-
another question I
If-
have, which I thought, which is maybe or may not be related to these, is you say that you train models on clean speech and this is a noisy speech.
Yeah.
So how was the speech made noisy? Was it already noisy during recording? Or was
No,
it
we assume
added
it's
to it?
clear during recording
Okay.
and training. So we train on
No,
clean
we
speech.
train the models. Now the
We
test
train,
speech
okay.
is noisy. So what kind of noise?
Well,
is
for
it?
example, just looking at, I have another plot. Just for example, there are many ways to guess whether there is noise or no noise in a band, but you look at the likelihood distribution. So this P of X in that band. So for all, the sum over all possible phonemes, if you look at the P of X, the entropy of the P of X is going to increase if you have noise. Right? You agree with me?
No, I
The
definitely
the entropy of the distribution of P of X is going to increase.
fine.
So I can say, oh, there is noise. So my model,
If you give me a result
okay,
which claim that it is immune or robust against noise,
well, I showed you
have to
results already.
specify what that noise is.
Can you describe
Well, it
the
can, that's the advantage. It can be any noise.
No. If,
I don't want to model the noise.
So what about competing speech?
That's not noise for me, and it's not going to solve that problem. I agree. It's not.
What noise did you use?
We tried many things: car noise, siren noise, factory noise, anything that is band limited, non-stationary. It will work. Now, it's not going to address the problem of wide band noise. It doesn't work. It doesn't help. This doesn't help for wide band noise. So the only assumption I do is that my noise is band limited.
I guess the other answer to your question
That's it.
is non-state.
That's if you want a model.
It moves around.
Because as soon as I work, my student finishes, another student finishes PhD, he did something very interesting I was talking about. That's whatever the kind of noise you have, okay? If you start looking at one narrow frequency band, all the noises look the same. It's white noise. You take car noise, factory noise, this noise, and then you look at the noise in one very small band, it's like white noise. Why can you say it's car noise or factory noise? It's just white noise in a subband, but it's band limited.
Go on.
Okay. Okay, anyway, I'm not going to spend much time on this, but basically this is what you have. I don't try to explain this. But then if you have noise, I had noise in one band, okay, white noise or whatever, then I'm going to, by doing this online unsupervised adaptation of my weights, well, these weights for the first, band 2 actually in this case, band 1 there, is going to be converged to 0 very quickly. You know, and we did it with all kind of noise and different bands. And so this is if we have noise in the third band, noise in the fourth band, and so on and so on. And we don't change the emission probability. So by doing this online adaptation, we are just going to basically to kill the band where there is noise. And we never try to explicitly detect where the noise is. Okay? Now, I still have something to talk about, much more interesting, which is a generalization of that, but okay.
You're saying that you require narrowband noise, but I guess
I never acquired anything. Okay, what do you mean?
require.
Oh, require, okay.
But wouldn't it also work if you have broadband noise as long as at least one channel will still be clean?
If we have wideband noise, well, I don't have time to discuss all the details, but what we do, first we do a processing that gets rid of wideband noise. So JRASTA is doing that very well for us. So we are trying to do a processing where we get rid of the wideband noise, but we stay in the spectral domain to do this multi-band thing. So we stay in the spectral domain, and then we do this multi-band processing. And first of all, we just get rid of convolutional noise and wideband noise. Is this answer your question, or are you saying if everything is noisy but one frequency?
The one band.
I think then multi-band is going to work. Yeah. Okay. Yeah. As long as the band which is not noisy is there is still some information in there. You know, if it is the fourth band and you are trying to recognize a vowel, of course you have lost the information. Okay, so what I was trying to do during this talk is a kind of overview of things that are going on in this multi-band, multi-stream thing. So I showed you very briefly this standard subband multi-stream, okay, that everybody is using now. I told you a little bit about product of errors rule, which is still controversial. I told you about full combination, where basically I don't make the assumption where the noise is. I just sum up over all possible positions of the noise. Now, I still had a problem, and I had this question this afternoon, how to define the subbands. So this is also a point that I had on my list of open questions for 2 years, and now we solved it. So how to define the subbands and how to define them, and since the beginning we had the feeling that ideally those subbands should be defined dynamically and should change over time. So we came up with this, so this is a further extension of the full combination where everything is adaptive now. It's called this HMM2, which is able to perfectly model the temporal and at the same time the frequency structure of the speech signal. So HMM2, in 2 words, is a mixture of HMM, and I'm going to tell you what it is. But basically, we have a temporal HMM in this simplest version of HMM2. We have the standard temporal HMM that we all know about, doing time warping and temporal integration for us. And then with each state of this temporal HMM, we have another HMM that we call frequency HMM, state-dependent frequency HMM, which is going to do the frequency warping and frequency integration for us. So basically, it looks like this. So this is how a regular HMM works today. So we get a speech signal, we take a 10 milliseconds slot, we get the spectrogram, which is a vector, right? And then usually we send it to MFCC, so we orthogonalize the data, and we send this to multi-Gaussian system density associated with each state. And now what we are doing is something like this. So we don't do this anymore. So we don't do this, we don't do that. So we have a vector of dimension d. And basically this vector is going to be emitted. Well, each component of that frequency vector is going to be emitted by a frequency HMM. So for a state qk, we have a Markov model, frequency-based Markov model with an initial state ik, okay, going to a state qk1. So the first frequency state for state qk, state 2, state j, and so on, okay? Topology can vary from an ergodic model to a bottom-up or top-down. This is still to be investigated, but this one works pretty well. Okay, and as a further improvement, but we haven't done it yet, but we are going to do it. We could also have for the next state another Markov model, and we can have some dependency of the density on the previous observation, which is going to smooth actually the decision when going from one state to another one. Okay, but otherwise what we have here, if we forget about this one, with each frequency state we have multi-Gaussians, if we like multi-Gaussians, but this is going to be a one-dimensional multi-Gaussian, right? Each state is going to emit one frequency component. Okay? So this HMM is going to do the frequency segmentation for you over frequency, if I do a Viterbi at least. Viterbi approximation, I am going to segment this frequency vector automatically.
I don't understand the arrows. Normally arrows mean time.
Yeah, on top there it means time. Well, usually arrows mean time, so in standard HMM here. So these arrows means time.
Yes.
These arrows mean frequency. How long I am going to, how many components of the acoustic vector I am going to emit on this state. So actually those, if you look at formants, we all know about formants, right? That's what I'm trying to model, and it does it very well for us, as you will see. Those transition probabilities actually are going to model the distance between two formants. Suppose I have only 3 states, right? 3 states, and I hope that each state is going to be associated with one formant, if we believe that formants are actually the important information for speech recognition, and I think we believe it, and more people believe it. You say no? Okay, but let's suppose we believe it, that formants are important for recognition. Each of the 3 states is going to automatically focus on one formant. So the transition probabilities here are going to measure the distance between formants, and we know that this is also an important information. Okay?
What's the observation distribution look like? It's a single-dimensional Gaussian.
Yeah? It's a multi-Gaussian. You assume it's a multi-Gaussian in the one-dimensional space.
So does this allow you how far up you get to place it?
So it's what?
I'm trying to understand what happens as you go down the chain. So you go in.
So you are going to start, so you start emitting the first vector, the first component. Then maybe the second one. Well, you are going to try to all possible segmentation of this spectral vector. You try all possible segmentation in capital J states.
Could you walk down the chain and describe it? Just start. So you
So,
go into the
so I am on the top. I hypothesize state QK. Okay, I want to compute the emission probability of QK. I observe a vector here at time n. The dimension of the vector is d, and it's constant. So instead of feeding the whole thing to a multi-Gaussian, I feed it to my HMM. So I first see the first vector, the first component. I compute its probability according to this the multi-Gaussian associated to this particular frequency state. Okay? Then I multiply it. Well, I multiply the second one, assuming it's emitted here or emitted there.
So you're sort of, are you assuming sort of left to right? So you had.
Well, it's bottom up or top down. This still has to be investigated. But interestingly enough, if you forget about this one, and if you have as many states here as you have component D, then it boils down into a regular multi-Gaussian.
So do you have like a factorial now instead of?
Yeah. But this is EM, you know. So if you go to our EDIAP web page, which was on my front page, first transparency, you have a report showing the extension of the EM algorithm. It's 10 pages of equations and so on, but easy. So it tells you how to train everything. The temporal HMM, this one, at the same time with an EM algorithm. That's a detail. So you train all those transition probabilities, emission probability, very easily, and it works very well. Okay, so do you get the idea? So this HMM2 now is going to compute immediately. So what you get at the output, maybe it's very small, there is a lot of information on this slide. What you get at the output of this frequency HMM is the probability of xn, the acoustic vector, given the state, qk. And maybe given the previous vectors, if you have an autoregressive HMM. It's just another way to compute an emission probability. You could have a Bayesian network, or you could have whatever, an ergodic Markov model, but here I believe that this Markov model is going to do the segmentation for me in subband. So and dynamically, it's going to change over state, and it's going to depend on xn. Everything I was...
This segmentation is.
I'm going to show you one.
As this time went downward, so you're producing. What do you mean segmentation?
Well, let me show you what I mean. This is one example. So this is a spectrogram. Believe me, this is by my student, you know. And you see it's a very poor quality spectrogram, but anyway. You see the formants there. I don't know, it's energy. And this is what I get automatically along my HMM2. This is the segmentation I get.
Segmentation means that a particular state emitted
so
a
state
string of a certain substring
of the frequency vector.
of the features.
Yeah, of the features. I prefer to stay in the frequency domain because I think it doesn't make any sense to do it in the FCC domain. So here you say that at the beginning here I had those components emitted by the first state, those ones by the second state, those ones by the third one, those ones by the fourth one. And this is going to change over time because I have different axes.
Yes, and then what?
Well, I get a segmentation in subband.
And what do you haven't said yet what I do with the segmentation.
Well, there are two ways, two possibilities. You just use the output of your frequency HMM as an emission probability, and you feed it to your Markov model, and you are done. So this is one solution. We tried this one. So far, it doesn't work better than the best subband model that we have. But this is just a beginning. Now I'll show you a second thing that we are doing. So is it clear now what we are doing here? Yeah? It's simple. It's very simple, but everybody is scared by this. But we can see why. Okay, but it's just another way to compute emission probabilities, really. It's okay, this is a nice, and you see, you know, if you see that this is following well, roughly the energy shapes and so on there, okay? Okay, so what we did, I am nearly done with my talk, because this is just a beginning. We have the theory, we have this initial results we call formant-like tracking. So we have many plots like this, where we show that actually the states here are segmenting the frequency domain into formant-like regions. We are not doing formant tracking really, because I just know, okay, the formant is in this region, but I don't say exactly in which region it is. So what my student did just before I left, and this is brand new, I hope she is getting more results while I'm speaking, but so we tried many things, and so far it was working very well, but it was not working much better than what we had so far. So what she tried very quickly, something very stupid. Listen to this one. It's extremely stupid. So we have 3 states. Well, she did it with 3 states. We just run this HMM2, and what we get at the output of the HMM, we don't use the probability, we just use the transition points. So we get 3 numbers, 3 integers. So if we have 20, well, in this case we had 15 critical bands, we get 3 numbers between 1 and 15. 3, 7, 12 for every 10 milliseconds. 3 numbers. And we use that as features for speech recognition. Okay? This is what we call the pseudo-formants. So this is for numbers 95. We know that it's not an easy task. So it's 3 format numbers for different signal-to-noise ratio. This is the baseline HTK system. Okay, the performance that we get, this is good. For numbers, it's 6% error rate. If you look at the state of the art, we are certainly very good. And then it quickly decreases when you start increasing the signal-to-noise ratio, well, decreasing the signal-to-noise ratio down to 26%. Then if you look at what we can do with those 3 magic numbers only, well, we get 45%, 46%, 40%. So basically it doesn't change, except at the very end where it starts collapsing at 0 dB. So it means that those 3 magic numbers that my HMM2 is finding are very robust to noise. And people who like formant will say, yes, the system is doing some kind of formant tracking. And so far, but this is just very, very rough what we did there. If we add those 3 numbers to those 39 MFCC parameters and we just feed them to HTK, that's what we are using now because it's faster, we get a significant improvement. Okay? So what we did also recently, just before I left, we can get much better than 26.5% if we do spectral subtraction. So if we look at the noise and we subtract the noise explicitly, so we can boost it to 66%, but even in that case, those 3 parameters there are still improving significantly the performance of the system. I'm basically done. This is the very last results that I got 5 minutes before I was taking the plane. But we like it, and it says that we will continue in that direction. I think I am done, apart from the usual conclusions, which are very general. So what we seem to be sure about is that multiband ASR doesn't seem to be inherently inferior to full band approach. So after all the experiments reported by many people, including us, we have never seen multiband system hurting performance. And if there is narrow band noise in the speech, it's going to help. Okay, in trading frequency, yeah, we still want to investigate this thing actually by using multiband. There is a potential for further improvement by trading frequency information for temporal information. There is still a lot of work to be done in recombination schemes, training, adaptation scheme. I presented this online unsupervised EM. Seems to work well. We still have to investigate it further. And yeah, we still need methods which are robust to noise, but still perform well for clean speech. So what we are, when those methods work well, but for clean speech, it's still better to use the regular approaches to get this better improvement, better performance. although usually it doesn't hurt much, even in clean speech. Okay, I'm done. Thank you for your attention. I'm done on time.
The last part of the talk depends on the fact that we are not able to use covariances, actually.
Yeah, I agree.
Right.
I agree.
If we knew how to use covariance, it may not work.
Yeah.
Well. But since we're using diagonal matrices, and therefore the Gaussian is a product.
Exactly.
Yes.
Now, if we knew how to model covariances properly, I could also still use this, but then I would have a fully connected frequency Markov model. And I would actually also model the correlation between the bands and so on. Right now, we just tried this top-down model, stupid because it made sense, and I felt that it would segment the spectrogram properly, and it seems that it does it. So, but yeah. Of course, if we could model the covariance, then we are done, yeah.
You take the log and filter back out those.
Yeah. Yeah. Well, we take more than that, actually. I didn't talk about this one, but we take the log, and then we take something which is not very well known, but I mentioned it this afternoon. We take also the frequency delta spectrum, which is much more robust to noise also.
So what I was going to say was,
So this is the frequency delta. This is the raster spectrum, so it's log. There is a log in there, so that's what we are using, yeah.
similar effects on it, since MFCC is a linear transformation of the log spectrum, can't you, you could define, it would be trivial to incorporate it in C.
I know. I have heard that already. We could, yeah. There are many things to try, you know, it's...
You would have a funny covariance matrix depending on the how much on S.
yeah. That's a good point.
Covariance DCT.
That's a good point, yeah. There are many, many things to do. It's Anyway, this was just in the trend of generalizing this full combination where we believe that we have found all the pieces except this dynamic definition of subbands. And this seems to do it. And it is going to, I think it's going to work, yeah. Sorry, it may, although I skipped all the equations and so on, it was maybe a little bit too much, or I tried it at IMA also, but it was really too much. Anyway, it's new. I think there is, because also if you have as many states as you have components, it's really equivalent to a multi-Gaussian.
All right.
Okay, thank you.